Okay, so we're going to start chapter 12, which is essentially an introduction to three-dimensional coordinates, better known as R3, or the three-dimensional Euclidean space. um, well, let's just dive in here. We're going to have three axes. So generally the one pointing sort of, you can imagine this x-axis pointing outside of the screen that you're watching. The y-axis going to the right, and the z-axis going up. And you can plot start off with, say, plotting some points. Plot, say, 1, 1, 0, for example. Let's call that point A. Well, you would travel 1 unit in the x direction, and then 1 unit in the y direction. So all points, by the way, so this is, points are going to be giving, any point is going to be an order, what's called an ordered 3 tuple of x, comma, y, comma, z. So here x is 1, so we go 1 unit in x, we go 1 unit in y, and we land right here because z, we're not traveling up or down at all, and this is the point A. We could have another point, say that we're going 1, 2, and say -1. Well, then what would we do? Let's use a different color for this point. So then for this point, we would say, okay, let's travel 2 units in the y direction after traveling 1 unit in the x direction. So we'd end up over here, and then we'd have to travel downward because these are all the positive. This is x positive, this is y positive, this is z positive. So we're going to travel down here to the point B, where B is the point 1, 2, -1. Similarly, you could, let's just do one last point here. You could plot some point C, which let's still do yet another color. So C is the point, say, 0, -2, and 4. So you would come out, there's 0 units in the x direction, and then you would go -2 units in the y direction, so -1, -2, say, and then you'd go up by 4 units, so 1, 2, 3, and 4. So you'd go up somewhere here. So let's call that's point C. So on and so forth. That you can plot lots of points in the following way. The question is, how do we graph some basic equations? That's what we're going to do next. So from points, generally in R2, so from points, we start with points. And of course, by the way, a very most important point here is just the origin, 0, 0, 0. Forgot about that. From points, generally in R2, if you're in R2, the XY plane, you will go to lines. Those are the next, generally considered, next most easy graph to consider. But in R3, lines actually take a bit more work. It's easier to go from points to planes. And we'll see why in just a second. But what are some basic planes that are sitting here? So let's redraw our x, y, z coordinate system. By the way, if you ever need to graph something, GeoGebra.com, I think is, or .org. I'll just write GeoGebra here. Is a useful, just look up 3D graphing, GeoGebra, and you'll get a website that can plot surfaces in 3 dimensions. But what are some important planes here to consider? So again, I'll try to shade this in with different colors. There is the plane that's sort of parallel to the x-axis. And I'm just going to draw some lines that look parallel. If you consider this, think of it like a wall. This is like a wall. This is the x, z plane. If you just took the x and the z axis and took the plane that was spanned by those, that's what's called the xz plane. In a similar way, if you sort of were on the floor, think of this as a room. If you're standing on you'll just say, okay, where's the carpet lying? This is kind of the carpet. This is the xy plane. And another wall here would be kind of over here, right above the y, and this would be the yz plane. So these are 3 pretty important planes that we'll make reference to fairly often. But the question is, what is the equation? What is the equations that correspond to these planes? And it's kind of the analog of the same thing in R2. And you can see here that so for example, for the xz plane, well, notice here that y is 0 there, everywhere. If you're on the xz plane, then that's precisely where y equals 0, and that is actually exactly the xz plane. So constant functions, so y is a constant, x is a constant, etc. These all correspond to planes. So in a way, constant functions, I don't want to say functions, constant curves, constant, okay, for lack of a better phrase, I'm just going to use constant functions are planes. We haven't really discussed functions in multiple coordinates yet, but you get the idea. Similarly, if you wanted to do the yz plane, probably guessed already, but for the yz plane, it corresponds to the equation x equals 0. Because when x is 0, that exactly corresponds to only things that have y and z running. And of course, the xy plane is when z equals 0. So we have those 3 items, and let's just do maybe one or two more examples. So let's plot, or let's graph. I want to say plot. I guess graph is a better word here. Graph, say y equals 2 and z equals, say, -1. Let's just do those 2, and then we'll move forward. So let's draw our xyz coordinate system. If y is 2, well, we go 1 and 2, and let me again use a different color for this. Well, we would have essentially, well, y is constantly 2, so we definitely are including, say, this line, but then we can also include the line, say, above here that includes it. So we actually get this entire plane of y equaling 2. And again, I apologize for the drawing here. If you want to see y equals 2 in a nice way, again, you can check out the GeoGebra site. But essentially, you can think of a knife sort of slicing along the y equals 2 plane, just slicing, and everything it slices is included in this graph, y equals 2. So this is y equals 2. In a similar way, you can consider z equals -1. Let's do that maybe off over here. And let me just draw, I think I'll first draw the plane. So this is the plane z equals -1, where the original axes would probably be sitting somewhere here, and you would travel down by 1 unit to get to the plane z equals -1. Okay. So constant, anytime you have a y equals a constant or x equals a constant, z equals a constant, you get planes. And notice, by the way, here, this is parallel to the xz plane, right? Because that's where y is 0. This is parallel to the xy plane. And similarly, if you were to plot x equals some constant, that would be parallel to the yz plane. Okay, I'll leave you guys to try and graph that. See if you're a better drawer than me. So those are some more elementary graphs. Let's do just one more here, and we'll stop this video here. So one last example. Let's plot what's going to be the surface x squared plus y squared is equal to 1. So normally, if we were thinking of this in just x and y, hopefully you recall, so in R2, this is a circle with radius 1 and center at 0, 0. But in R3, well, we still are going to include that. So we're going to get the circle here sitting on the xy plane. But then z, this allows z to be any value you like. Or in other terms, z is what's called a free variable. It's free to be anything. So you actually end up with these circles for every z value that exists, and if you include every single z value, you actually get this infinite cylinder, what's called a circular cylinder. So this is actually the surface, and it's literally the surface in the sense that it doesn't include the inside. So this is what's called a circular cylinder, and it's hollow. Right? The inside is not included, but the surface hollow. Only the surface is present. It's not a solid object. You can think of folding a piece of paper. Okay, you can think of folding a piece of paper into the shape, and that's the surface, into this shape. That's what I mean by the surface only. Okay, I will leave you here with a little exercise, which is kind of similar. So graph the following two things. Y squared plus z squared is equal to 4. And then go ahead and graph the following, I'll just call it a set S, which is the set y squared plus z squared is equal to 4, and x is equal to 1. Okay, and we'll start the next video with that particular example.